1988. He held the position of Head Knowledge and Technology Management Division and Head Computational and Theoretical Fluid Dynamics Division at the time of his retirement on superannuation. He has a Bachelor of Technology in Aeronautical Engineering from IIT Kanpur, Master of Science in Aerospace Engineering from Cornell University, USA, and PhD in Aerospace Engineering from IISc Bangalore. His area of interest are computational fluid dynamics and grid generation for aerospace applications. He has around 70 research papers in journals and international and national conferences. He was a research visitor and also scientist in the University of Wales, Swansea, United Kingdom during 1990 to 1991, and again in 2001 to 2002. He has been actively involved with the CFD division of the Aeronautical Society of India, holding the positions of General Secretary from 2004 to 2008, Vice Chairman from 2008 to 2014, and Chairman from 2014 to 2021. The CFD division organizes the annual AESI CFD Symposium in August every year. So, sir, I welcome to this platform to share your presentations. And today's sir's topic is generation of structured and unstructured grids for CFD analysis. Welcome, sir. Now you can share your screen.
Thank you. Thank you for the introduction, and I'm very happy to be here. Am I audible?
Yeah.
Yeah. Good to see you, Dr. Majumdar, after a long time.
Sir, you can switch on your video and you can talk, sir, with the video. Others will switch off. Yeah.
Switch off the video.
No, sir. Madam, sir, your video, let it be there.
Okay.
No problem.
Okay. So I'm very happy to be here for this course on CFD. And
Sekhar, sir, you can switch off your video, sir.
One second, Dr. Majumdar sir.
Switch off for you. Yeah. Okay, sir, you can present now.
Yeah. So I'll just, I have a presentation on this grid generation. So I will go through the basics, and if some of the people here are already familiar with the subject, they may find some of the things repetition, but for the sake of completeness, it has been made as a presentation starting from the very beginning. So let me share my screen now, and then we'll go ahead. Okay, is it visible, the presentation?
Yes, sir, visible.
Okay. So title is Generation of Structured and Unstructured Grids for CFD Analysis. And this is my area of work for the last 30 years. And in National Aerospace Laboratories, our focus has been on aerospace applications. So whatever you see will be focused more on aerospace, but the techniques are valid in general. So let us start right from the beginning. First of all, why do we need grid generation? So as you will see in the lectures, and some of you may already be aware, normally in CFD, we use finite difference or finite volume or finite element techniques. And all of these techniques require the computational domain to be discretized into a set of points. And this is called the computational grid. And these are the points at which the flow quantities are calculated. Now, the accuracy of your computation is dependent very strongly on the grid quality. So whatever techniques you have for grid generation, they must allow you to control the grid structure and the distribution of grid points so that you can get the sort of grid that you need for the type of solution that you are seeking. there are two main categories of computational grids. One are body conforming grids, where the grid lines will not cross the boundary. So if you have an airfoil or an aircraft, the grid lines will be conforming to that boundary and will not cross it. The other category is called non-aligned or Cartesian grids, where you will allow the grid lines to cross the boundary. So there are advantages and disadvantages in both these methods. Where you have body conforming grids, it is very easy to apply the boundary condition. If you have Cartesian or non-aligned grids, the boundary condition application is a bit difficult, but the grid generation part is easy. So it's a trade-off whether you want to have easier boundary conditions or you want to have easier grid generation. Another category is that which is called overlap grids, where essentially if you have multiple components, you will generate different grids and then the grids will overlap. And then you will need to have some sort of interpolation because since they are not the same grid, the flow values will have to be interpolated. And this method is sometimes used when the grid generation becomes very difficult. But generally, the techniques that are used for interpolation make it not that accurate. Then we can also classify grids into what we call structured grids and unstructured grids. So when I discuss structured and unstructured especially, I will give some ideas about what is the basic difference between these two categories of grids. So structured grids were the most commonly used. And now, of course, in the last 2-3 years, we are seeing a lot of use of unstructured. But before that, we were primarily using structured grids. The advantage of structured grids is that they have an inherent data structure. And this allows you to make very efficient flow solvers. And with something called the multi-block approach, which I'm going to explain later, you can generate grids for very complex shapes. The drawback is that structured grid generation takes a lot of time. And especially when you do multi-block grid generation, a lot of time and effort is required. Another disadvantage of structured grids is that if you want to do grid adaptation, it is a bit more difficult. I will explain that further in the talk. So for structured grid generation, we have two main methods, algebraic and elliptic. So algebraic methods are very fast, but they don't have the smoothing properties which elliptic methods have. So algebraic methods, you have to be very careful that your grid quality is maintained and also you don't have grid line crossover and those sort of problems. So the present trend is to use a mix of the two, which is that you start out with algebraic methods for the initial grid, which is very quick. And then depending on the requirement, you can use the elliptic method for smoothing the grid. As I just said, unstructured grids are becoming very popular now. And the reason is that for a very complex shape, you can compute the grid very quickly. So the time that is spent in doing structured multi-block is saved here to the extent that if structured multi-block grid took days, you will take the similar unstructured grid could be done within an hour. So that is the sort of difference in time we are talking about. And also then in unstructured grids, the data structures are such that grid adaptation can be easily done. However, the flow solver has to be written specially to use unstructured grids. So grid adaptation is a method by which you concentrate grid points in regions of high flow gradients. So wherever there is a high flow gradient, you need points to be close so you can pick up those gradients. And it is difficult to have a very, very fine grid in the entire domain because your grid size will become not possible to handle. It will be too big. So you would like a grid method by which you can move points where needed and have a sparse grid where there is not much happening. So for grid adaptation, again, there are two main techniques. One is called point movement, where you will move the grid point towards the region where you want to concentrate them. And the other is called point enrichment, where you will actually add grid points where you need them. And the way the structured and unstructured grids are done, if you have a structured grid, it is easier to do mesh movement. Whereas if you have an unstructured grid, it is easier to do mesh enrichment. So some thoughts on grid generation. See, grid generation is not the final goal. It is an intermediate stage. So in the entire flow simulation process, it is one of the stages that is there. And ideally, it should be very fast and it should be automatic and it should require minimal user intervention. However, experience shows that if you have a very complex three-dimensional geometry, the grid generation takes a disproportionate amount of time. A lot of time is spent on the grid before you can actually do the flow solution. And some amount of user expertise is required because it's very difficult to get a perfect grid in your first time. And it will require a lot of experience to handle the sort of grid that you need for the sort of flow you're computing. And even now with all the tools at our command, very complex geometries, the grid generation facility becomes the bottleneck. The solver is capable of doing that problem, but you have a problem in getting the grid done. So we need software which does fast and automatic and can be used by non-expert. So a lot of packages are available now which are being routinely used across the CFD community. But a word of caution that despite all these packages, you would still need a fair amount of experience before you can use them effectively and use all the capabilities that there are in those packages. So after that sort of basic introduction about grid generation, I will start discussing structured grid generation. So as I said, there are two main categories for generating structured grids. One is the PDE methods, in which you actually solve a system of partial differential equations to generate the grid. Okay, so here it is a numerical method in which equations are solved to generate the grid. Then you have algebraic methods, which use some sort of an interpolation function to generate the grid lines from the coordinates that you have specified on the boundaries of the domain. So you will have a computational domain. You will have boundaries on that domain. On that domain boundary, you have to specify some grid points. Based on those grid points, either the PDE methods or the algebraic methods will generate the grid within the interior of the domain. So let us look at some of these methods in a bit more detail. So first we will look at elliptic equations. So this is a very popular approach. The advantage is that you can get very good and smooth and high quality grids. The disadvantage is that it is computationally more expensive than the algebraic methods. So the basic idea of this method is that the physical domain is mapped to a rectangular computational domain. And we represent these by 4 boundaries. I'm talking in 2D now. So xi going from 1 to xi max and eta going from 1 to eta max. So these are the 2 boundaries. So the grid will consist of a family of xi constant lines and eta constant lines. And then when you map this computational domain back to the physical domain, you will get the required grid in the physical domain. So there is this one-to-one correspondence between physical space and computational domain. So we can start with these Poisson equations, xi xx plus xi yy, and on the right hand side we have what we call the grid control functions. Now what we are trying to do is get the grid. So we are solving for x and y. We are not solving for xi and eta. So we transform these equations so that we solve for x and y. So you will get this set of equations where it's explained what are A, B, C, J is the Jacobian. And these set of equations have to be now solved by a numerical method. And appropriate boundary conditions. So these being elliptic equations, you need to specify the boundary conditions on the entire boundary and solve for the interior points. So we can write in a more general form where R represents the X and the Y coordinates. And this is the equation. Now, this can be solved very easily using central difference discretization. So these being second order derivatives, you can use central difference discretization for the derivatives and use standard scheme like successive over relaxation scheme to solve the equations. And if you look at the numerical methods, there are things called approximate factorization and similar schemes, which will make it more efficient to solve the problem. Now, the grid control functions are used to control the grid point spacing as well as the angle of intersection of the grid lines. So I'll try to demonstrate how these grid control.
Hello. Hello. Is it audible, sir? Hello.
Sir, are we audible? Sir, I think. Sir, just wait, sir. I think you have been muted. Yeah.
Hello?
Sir, now it's okay, sir. Please.
Okay, yeah. So these grid control functions give you some control over the grid point spacing and things like that. A lot of functions are suggested. I will just not going to the next screen. Then it will not go to this point. Huh?
Sir, any problem?
1 minute, some sharing, something happened. 1 minute.
Okay, no problem.
Okay. Let's see. My slides are not moving. Just 1 minute.
Sir, don't worry. Please unshare and again share. It will work.
Please stop share.
Please unshare and again share. It will work.
This. Share this again. Some problem in moving the slides. I don't know what it is. the control functions can help you to generate the kind of grid that you're looking for. Now, if you want to generate a C-type grid around an airfoil, then you see the top figure. There is a computational domain and an outer boundary is defined. And this is actually, you have to make a cut and open it out into the computational, from the physical domain to the computational domain, then generate the grid in the computational domain and map it back to the physical domain. So if you can see now, the A to B is going around the airfoil, and then B to C is on the cut line. Then C, D, E, F is the outer boundary. F to A is back on the cut line. And those points are shown in the rectangular domain at the bottom. And by this, you can get a grid which will look like this in the physical domain. Now here, if you notice that behind the airfoil, there is a cut line, and you can see that there is a sort of kink in the grid. The grid lines are not smooth. They are coming from both sides and meeting at an angle. This is happening because I have put in Dirichlet boundary conditions there, which means that the points at the boundary are not allowed to move. They are fixed there, so you get this sort of a kink. Now we will look at another type of grid. Suppose you want to generate an O-type grid around an airfoil, then this is a sort of computational domain you will have. A to B is on the surface of the airfoil, then B to D and A to C are on the cut line, and then D to C is on the outer boundary. So if you generate this grid and map it back to the physical domain, you will get this kind of a grid, which is an O-type grid. And here you will see that we have put periodic boundary conditions on the cut line. So it is a very smooth grid. Again, the effect of the control functions are shown here. The left side is elliptic equations without the control functions. The right side is showing with the control functions, Thomas-Middlecoff control functions. And you can see that in the right side grid, there is a clustering of the grid lines near the airfoil, whereas on the left side grid, the grid lines are spaced far away from the airfoil. So this is the sort of control that you can have with control functions. And this is just one example. There are many control functions available in literature which do a variety of control tasks. So this elliptic equation method can be easily done in 3 dimensions also. So you will have the 3-dimensional Poisson equations. Again, you can write it in the form that I've shown there, where R is the X, Y, and Z coordinates. And these are the expressions for all the other constants that are shown there. And in a similar way, you can solve these equations for X, Y, and Z in 3 dimensions. And you can get a 3-dimensional grid. And again, I have suggested some grid control functions, which are given in literature and which you can use for controlling your grid points. So that is elliptic equations. Now I'm going to describe one other method of structured grid generation, which is called conformal mapping method. Now, conformal mapping method can be used for grid generation, but for very specific type of geometries, because there the complex domain is mapped mathematically into a simple domain. You can generate a grid in the simple domain and map it back to the actual domain, and you get the grid. So one example that I'm showing here to generate a very good quality O-type grid around an airfoil. So people who are familiar with aerodynamics will recall that there's something called a Joukowsky mapping, which maps a circle in one domain into an airfoil in the Z. So you go from a circle in the zeta plane into an airfoil in the Z plane. And this Joukowsky mapping gives you an airfoil with a cusp trailing edge, which means that the angle at the trailing edge is 0. It is like going into a straight line. So this mapping can be written in the form that I have given below also. And there is a generalized form of this mapping, which is called the von Karman-Trefts mapping. And this gives you an airfoil with a finite trailing edge of lambda. And this is the form in which this mapping is given. So using this mapping, you can take any general airfoil and map it to a near circle. Then in the near circle, you can generate a polar grid. And when you generate that polar grid and map it back to the physical domain, you will get a very good quality O-type grid. And this is one example that I've shown here. And you can see that everything is intersecting, all the grid lines are intersecting at right angles, which is because of the conformal mapping feature. And this can be used for very specialized geometries. So disadvantage is that this is not a very general method. It cannot be easily extended to 3 dimensions. And earlier in the history of grid generation, they were used for some complex shapes, but now because other methods have taken over, these are not very common. And different mappings can be used for different types of geometries. Then we have algebraic methods, which are computationally very fast, and they allow very precise control of the grid point spacing. The disadvantage of algebraic methods is that sometimes the grid is not inherently smooth and it can have discontinuities. And in general, algebraic methods involve some sort of interpolation between points on opposite boundaries. So you will have to define your computational domain. You define the points, boundary points, what are the coordinates, and then you do some sort of an interpolation to get the grid in between. However, there are very, again, specific algebraic functions that you can use to generate grids for certain geometries. So I'm going to describe one of these methods, which is to generate a C-type grid around an airfoil. And this generates a grid which is a family of hyperbolas. So this grid is very good for 2D 2D viscous calculations for an airfoil. So what is done here is that, as you can see in the figure, the airfoil is shown as eta min boundary, and the outer boundary is a eta max boundary. And then you have downstream boundaries which are zeta min and zeta max, xi min and xi max. And the xi constant curves are a family of hyperbolas. And then you will get x and y values of the grid points by these two equations, where you have these constants. So why were hyperbolas chosen? They have these advantages, that in the far field, they become almost straight lines and look like radial lines. And the degenerate case of a hyperbola is a straight line. And you can patch these two regions together. So these are some mathematical advantages of hyperbolas which have been used to get a grid generation package. And we see that theta varies from pi by 2 to 3 pi by 2. And there are two degenerate cases. These are some details that you would need if you wanted to write a grid generation code for this. And then you have these parameters which will give you the control over the grid. And as it says here, this parameter b minus a has a very large influence, etc. You can algebraically see that you can get the values of these constants where you have the chord length, and then you will get the value of theta, which is given here. So after you do all this algebraic work, you can derive these equations for eta min and airfoil surface, and for x and y. So eta min you will get at the point of intersection of the hyperbola and some far field boundary. Then you have to do a distribution of eta between the minimum and maximum. This will give you the points from the airfoil to the outer boundary. And the way you do this distribution gives you your control of the grid points. So if you are doing a viscous calculation, then you can do this eta distribution such that you get clustering near the airfoil where you have your boundary layers, and you can let it spread as it goes towards the outer boundary. So this is one example of the sort of grid you get using this method. So this is a C-type grid around an airfoil. The outer boundary is taken as a portion of an ellipse. And if you see the close-up, you can see the grid lines coming out from the airfoil. These are the hyperbolas. And then you can see that some clustering has been done near the nose of the airfoil, and the grid lines have been pulled towards the airfoil surface to be able to capture the viscous layers. So this sort of an algebraic method, once you get it to work, it is very, very fast, and it can give you a very good quality grid for specific geometries. There is one more method which is slightly more general than what I have described earlier, which is called transfinite interpolation. So this again is just interpolation between the boundary data from one boundary to the other. So again, if you represent the boundaries by eta equal to 0 and 1 and xi equal to 0 and 1, then you can define these interpolation functions along those lines. And if you add this up, you will get the sum of these two expressions, which is this interpolant. However, if you actually do this, you find that you will not recover the boundary values. So you have to add a third expression, which is shown here, RC. And if you add all of these up, you get the total interpolant, which is this expression. And from this, you can interpolate the values between the two boundaries and get the grid in the middle. Now, transfinite interpolation methods, you can extend it so that the boundary slope data can also be taken into account. And I have just given this here, how you can include the boundary slope data and then get a function for the interpolation. And there will be some conditions on the alpha and beta. And this method is also possible to extend to 3 dimensions. So this is, in a way, the algebraic equivalent of the elliptic equations, where you can write a general method which is valid in 3 dimensions, which will take the boundary data and interpolate to the interior and give you your grid in the interior. So this is a very fast method, but because it is an algebraic method, there are some issues related to sometimes the grid lines may intersect, or you may not have very continuous lines, or you may have other issues. So it has to be used with care. So this is just one example I'm showing of an O-type grid generated around an airfoil using transfinite interpolation. So most of the examples I've shown you so far are 2D. Now, in real life, you have to actually do 3D configurations. And there are many 3-dimensional solvers for structured grids. And many of our organizations have concentrated on structured grid generation. However, before you go to full 3D grid generation, there are some techniques that can be used for relatively simpler geometries. One method is called the grid stacking method, which I will explain. So if you have a simple shape like a wing, then you can generate a 3D grid by essentially generating 2D grids at the sections and stacking these grids together and getting a 3D grid. Now the sectional grid can be generated by either algebraic methods or elliptic methods, or combining the two methods. And grid stacking method, if you take care, you can also extend it to more complex geometries. So here I'm giving an example. This is for a wing geometry. It's a CH type grid where the algebraic grid generator I explained earlier for the C type grid has been used at different wing sections. Then these wing sections are these 2D grids are combined together, which is called grid stacking, and you can get a high quality 3D grid relatively quickly for a wing. Similarly, we can do an OH type grid on a wing, where the O grid is generated using an elliptic grid generator. Again, at each section, you generate a 2D grid, you stack them together, and you get a 3D grid for the wing. This is a similar type of grid done for a delta wing, where it is an HO type grid, where the direction of the O grid is different. And here what we did was we did a hybrid algebraic elliptic grid generator, where the one family of grid lines was generated using an elliptic grid generator. The other family of grid lines, which goes from the boundary of the wing to the outer boundary, was done using an algebraic method, so that you could get the sort of grid clustering that you need near the surface of the earth. These are some examples for slightly more complex shapes for a launch vehicle kind of configuration, where again we have used the grid stacking method. But as you can see, the geometry changes from 3 cylinders to 2 cylinders and 2 singularities to 3 singularities. So again, with a little bit of effort, you can generate a 3D grid using grid stacking and 2D grid generators. Similarly, for a slightly more complex launch vehicle configuration, where you can see that there are essentially 5 bodies, which then go to 1 body and 4 singularities, and finally to 5 singularities ahead of the upstream of the body. So this grid stacking, of course, cannot be used for aircraft-like shapes, because you will not have the grid quality that you need. So you need to do what is called 3-dimensional multi-block grid generation. What is multi-block grid generation? So what we are doing here is that in any grid generation technique, you are essentially mapping the physical domain to either a rectangle in 2D or a cube in 3D. And if you have a very complex body, it is difficult to do this. So we break the domain, the physical domain, into a number of blocks. And a simple grid is generated in each of these blocks. And you map it back to the physical domain. And the way you distribute these blocks, the way they are connected to each other, determines your grid connectivity. However, to use a multi-block code, you need to have a flow code which can handle multi-block grids. Multi-block grid generation involves essentially the following steps. First, you have to arrange your grid blocks. So this will be based on geometry, flow features, some amount of experience that you have, and the sort of flow solver you're using. And adjacent to the surface, the way you arrange your blocks, you will get the surface grid. Then you have to create a grid on all the block faces. Then you have to generate a volume grid inside each of the blocks, and then define the block connectivity in the way that the flow solver requires. So to make multi-block grid generation easier, a combination of elliptic and algebraic methods are normally used. So what you will do is in each block, you will first do an initial grid, which is algebraic, using something like transfinite interpolation. And then you smooth this grid using the elliptic equations and control functions as required. So nowadays, if you see, many commercial packages are available, and many of them are user-friendly. In NAL, we use something from Pointwise, which was earlier called GridGen. And this has a graphic interface, which allows you to visually create the blocks and get intersections of the components, control the grid points, generate a quick initial grid. Then you can check within each block whether there are any negative volumes which are caused by grid lines crossing or skewed cells. And then you can do some grid smoothing and then assemble the blocks in the order that you wish. So this sort of a package makes it much easier to do multi-block grids, and many options for smoothing, many options for assessing grid quality. So these things are required for if you want to use software. Now I'll just show a couple of examples. This is a 2D example where you have a 3-element airfoil. And in order to generate the grid around the airfoil, you can see that different blocks have been formed. There is one block around the main airfoil. There is one block around the second airfoil. There is a third block. So you can generate these different blocks. And within each block, you can generate an independent grid and make sure that your connectivity of the blocks is defined properly. And your grid generation, grid solving software can handle such a grid. Similarly, if you want to go for 3D, this was one in-house code that we had developed at NAL. So we used a 30-block grid with so many grid points. And this is for a half aircraft configuration. So you can see the way the grid points are distributed. Those represent the different blocks and the different block faces that have been used. So another geometry here where in addition to the wing fuselage, we added a stub wing. And then again, the number of blocks increased. And we used a constraint that one block face can only connect to another block face fully. That is, there is no partial connection of the block faces. Now, if you use that constraint, your number of blocks begins to increase very rapidly. So we went from 30 blocks to 64 blocks for this addition of one small component. Then we realized that this strategy is not very useful. So we made a strategy in which a block face can connect to a portion of an adjacent block face. So this makes the connectivity more complicated, but it makes the grid generation easier. So for this sort of an aircraft configuration, you can do a 33-block grid. Just to illustrate how complex it sometimes gets, this is how the blocks are arranged in this 33-block grid for the half aircraft. And this is something that you have to do yourself, decide what are the blocks, each block goes from where to where, and what is the domain, and how it connects to the other block, and cross-section wise and all that. This connectivity has to be done very carefully. So this is just to show at different cross-sections how the blocks will be connected. You have to make sure your IJK coordinate directions are correct. You have to make sure you have a right-handed coordinate system everywhere, how the blocks are connected, because in the flow solver, these blocks have to communicate with each other as you solve the problem. This again using the commercial package for an aircraft half-body configuration, how you would generate a structured multi-block grid. So as you can see, it is possible for fairly complex configurations to be gridded using multi-block method, but it will take time. It takes a bit of experience in understanding how this should be done. And it is a process that if you change the geometry, you have to repeat. So the grid generation takes quite a bit of time in this method. Now, having talked for a long time about structured grids, I would like to go into unstructured grids. Hello? Audible?
Yes, sir. Audible, sir.
Okay. So fundamentally, if you look at any grid, it consists of a set of grid points, and these grid points are connected to each other in some manner. Now, when you have a structured grid, this connectivity is not explicitly defined. So you store the points in a matrix in such a manner that The points in the matrix are the neighboring points, and that explains how these points are connected to each other. However, when you talk about an unstructured grid, this connectivity has to be explicitly defined. So a structured grid can always be represented as an unstructured grid, but it is not true in the other way. Okay, I'll again have to reshare 1 minute. It doesn't move. Stop share. I don't go to the slideshow. I go to the PowerPoint. Try to electric equations. That's the problem. Grids. Current slide. Okay, so let me explain how this is done. Let's look at a very simple grid. We have a 3x3 structured grid. So there are 9 points, and we store the x and y values in 2 arrays. X of I comma j, y of I comma j, and I and j vary from 1 to 3. So in these 2 arrays, I can contain x and y values of all the 9 points in the grid. And I know that x point 1 comma 1 connects to point 1 comma 2 and so on. I don't need to explain how it is connected. But if we want to represent the same as an unstructured grid, then what we do is we number the points from 1 to 9 and store their x and y values in array x of I, y of I going from 1 to 9. And then we have to define a connectivity matrix. So this connectivity matrix can be done in a number of ways. It can either be a set of edges or a set of cells, and we can define how the edge or cell is formed. So let's look at this. I have got 9 points. I number them from 1 to 9 in this manner. And then I define a connectivity matrix where there are 2 ways. One is I say there are 4 cells, and the cell consists of 4 nodes, and these are the 4 nodes that form that cell. Or I can say that there are 12 edges, and each edge is made of 2 points or 2 nodes, and those are the nodes which form that edge. So I can list cell number 1 to 4, the forming points of each cell, or I can list edge number from 1 to 12, and I can list the forming points of each edge. So this is how you would define the connectivity in an unstructured grid. So you have 9 points. For each point, you define the coordinate x and y. And then in this matrix, you define how those points are connected to each other. So these data structures are very general. If you use the edge or the cell data structure, it can define an unstructured grid with any kind of cell. And the advantage is that such a data structure gives you flexibility for adaptation of the grids. However, this explicit connectivity definition means that you require more storage, computer storage and memory, and your flow solver coding becomes a bit more complicated because you have to now get the connectivity each time you are solving the equation for the cell or the edge. Now, one of the methods for generating an unstructured grid is called Delaunay triangulation. And historically, this was a method that was used to connect a given set of points to obtain an unstructured grid consisting of triangular cells. Okay. So the point I'm emphasizing here is that classic Delaunay triangulation means you have a set of points and you want to connect them into a set of triangular cells, then this method can be used. So if you have a geometry which is very complex, then around each simple component, you can generate a set of grid points independently, and then take this entire cloud of points and use triangulation to connect all of them into a consistent set of triangular cells. Now, this is mathematically, the Delaunay triangulation goes like this. For each point, you define what is called a Voronoi region. This is defined as a region in the space that is closer to that point than to any other point. Okay. So what this means is that it is some sort of a polygon such that each side of this polygon is midway between the 2 points that it separates. So you will get a polygonal shape around each point, which is closer to that point than to any other point. And once you do this Voronoi, it's called a Voronoi tessellation, then across each of those sides of the polygon, if you connect the points, you get a triangulation, which is called a Delaunay triangulation. And this has certain very good mathematical properties, which makes it an ideal grid generator. So this is one property, that within a triangle, if you circumscribe it with a circle, no other point will lie within that circle. And for each triangle, there is a Voronoi vertex associated, which is at the circumcenter of the triangle. And you can describe this by a data structure which gives, for each vertex, the points which form the triangle and the adjacent vertices. Here I've tried to illustrate how the Voronoi region and the Delaunay triangulation come in. So the points that you see labeled as V1, V2, V3, V4, these are the Voronoi vertices. The points labeled 1, 2, 3, 4 up to 9 are the actual grid points. And then you can see how the triangulation is done. And for each Voronoi vertex, you have the forming points of the triangle and you have the neighboring vertices. So you describe it using the data structure, which is shown in the table. So this is an algorithm which is used to do a Delaunay triangulation. So the point to be noted is that it takes one by one each point. So you start with 4 points, and then you start adding, you create a Voronoi diagram, and then you start adding points one by one and retriangulating until you have added all the points. So this, I've just listed out what are the steps that are used. So if you were to write a code to do Delaunay triangulation, you would have to code this, go step point by point, read in a point, triangulate, read in a point, triangulate, and repeat. And after you have added all the points, some of the triangles may lie outside the domain. So these have to be deleted. And sometimes it may happen that you do not recover all your boundary edges. So there are techniques to recover the edges. Now, this particular method that I have described is not very flexible because it is asking you to generate the grid points using some other method and then doing the Delaunay triangulation of those points. So to make it slightly more flexible and easy to use, a point creation algorithm was used, where you can instead of reading the points from a list, you can create points as you go along. And the points can be added based on the boundary point spacing that you have used. So what this does is that from the boundary point spacing, you can have some sort of a point distribution function which represents the grid point spacing. Then you do a Delaunay triangulation of only the boundary points. Once you have this Delaunay triangulation, then for each triangle, at the centroid of the triangle, you define a new point and then find that point distribution function by interpolating there. And you see if that point meets that requirement. If it doesn't meet that requirement, then you add that point. If it meets that requirement, you don't add that point. So this gives you some control over how the grid points are going to be distributed during the triangulation. So this method is actually very easy when you have complex geometries, because what it means is you just need to define the boundary point distribution, and this algorithm will do the interior triangulation. So I'll just give you a couple of examples. The first example for a single airfoil is a Delaunay triangulation where the points have been given to the algorithm. So you see some sort of a structure. You can make out that probably some kind of an O grid has been generated, and then those points have been given to the triangulation, and it has done the triangulation and some smoothing to move the points. But there is a background structure that is there. The second is a 2-element airfoil, where again you can see that around the main airfoil there is something like an O-type grid generated. Then around the second flap there is a smaller O-type grid generated, and these two point sets have been put together and then triangulated. So again you can see some sort of a background structure, although these are unstructured grids. Now these are grids which have been generated using the point creation method. So this is what we think of when we see an unstructured grid. The first one is showing a single airfoil with, and you can see now that there is a clustering of the points in the vicinity of the airfoil, especially around the leading edge and the trailing edge. And then as you move away from the body, the size of the cells increases. So this is the sort of control that you want, that near the airfoil you have a clustering of points, and as you move away from the airfoil, the points can be sparse and the grid size can be reduced. The second one shows a 4-element airfoil. So again, you can see how the gridding has been done. There is a lot of grid points concentrated in the nose of the main airfoil and around the slat. And then the two flaps, again, you can see how the points have been distributed. And you notice how, as you move away from the airfoil, the size of the grid cells increases and the spread of the points is there. So this is how you can generate very quickly unstructured grids for very complex shapes based on the boundary point distribution. Now here I have not shown the outer boundary, but the outer boundary is fairly far away. It might be some 30 to 40 chord lengths away. And the point distribution on the outer boundary will be very sparse. So as you move away from the airfoil, you will find that the grid cells become larger and the number of points becomes less. And this concept of Delaunay triangulation can be extended to 3 dimensions. In the 3D domain, you will have tetrahedrons. So there what you have to do is you first generate a triangular grid. For example, this is a wing and a symmetry plane. So you will first generate a triangular grid on the symmetry plane and the wing surface, and similarly on the outer boundary. And then using that boundary point distribution, you will generate the tetrahedral elements. And again, you can see in the sectional view that near the wing, the elements are small. And as you move away from the wing, the element size becomes larger. So this was some idea about unstructured grid generation. Now, I would like to give a little bit of time to what is called grid adaptation. Now, what we mean by grid adaptation is that, as I explained right in the beginning, in your solution, there will be regions where there are large flow gradients, where you need to have more grid points. And then there are regions where not much is happening. The flow is fairly calm. So you do not need to have large number of grid points to resolve that flow. Now, generally, when you solve a problem, you are not aware of where this is going to happen. You have some idea. Based on that idea, you will distribute your boundary points. But if there is something happening within the domain, at the beginning of the flow solution, you do not know what that is. So you have to do some sort of grid adaptation, because it is not possible to do a very, very fine grid in the entire domain. You will have millions of grid points and it will take a huge amount of time to solve that problem. Plus, you are overkill in many regions because essentially nothing is happening and you've got large number of points there. So grid adaptation is a method by which there is some interaction between the grid and the solution on that grid. So it is 2 steps. It means you take an initial grid and generate a solution. Then in that solution, you identify regions where the grid may be inadequate and you need to add points. Then you need to adapt the grid in those regions and again solve. So it is a process where you move between the flow solver and the grid and do the adaptation to suit the solution. So how do you decide what is the criterion for adaptation? That itself is a major topic of research, and people have gone and found many different variables that you can use to decide where you want to do this. But it is generally some sort of a gradient. So you could say where there is a large gradient in the velocity, or there is a large gradient in pressure, or there's a large gradient in density. Those are the regions where I would like to add more points to be able to pick up those peaks and get a better resolution and a more accurate solution. So I think I explained this in the beginning. There are 2 main ways. One is called grid point redistribution and one is called grid refinement. Excuse me. So in general, the data structures that we use, in a structured grid, it is easier to do redistribution. And in an unstructured grid, it is easier to do refinement. One of the problems with redistribution is that when you move the grid lines towards some region, you are necessarily making some other region sparse. So you have to very judiciously see whether you are doing it properly. But the data structure is such that if you want to add a point in between, it becomes very difficult. So as I said, grid redistribution involves movement of grid points, but the adapted grid will have the same number of grid points as the initial grid. So you're not adding any grid points. You're just moving the grid points from one region to the other. However, when you do grid refinement, you are adding points. You're inserting points in the region. But if you are using an unstructured grid, this involves only a small change in the connectivity matrix. So with unstructured grids, it is easy to add points wherever you want without worrying about any problem in the data structure. Now, in the grid refinement process, the way it is done, normally you will do a initial grid using the grid generator. And after that, the flow solver itself will do the adaptation. So what it means is that you read in the initial grid, you generate a solution, and then after you have got that solution, the flow solver itself will determine where you have regions of high gradients, and then it will add points to those regions and continue the solution. So this can be a multi-step process. You can keep adding points and do 2, 3, 4 rounds of grid refinement. So looking at the data structure that I had shown earlier, which is the edge or cell data structure. So if you're doing finite volume methods, what you can do very easily is add one point at the center of an edge and divide the adjacent cells and then make the corresponding changes in the connectivity matrix. And to decide whether you should divide that edge or not, you can look at, for example, gradient of the density. So here what you would do is you would have a parameter which is user defined. So you say if the density gradient across this edge is larger than this parameter, this is input parameter, then please bisect this edge and bisect the adjacent cells. If it is not meeting that criterion, then you leave that edge. So after getting the solution, you will go to each edge, get the value of the density at the points which form that edge, then calculate the gradient, decide whether it needs adaptation. If it needs adaptation, add that point there, modify your connectivity matrix, and then go to the next edge. So this parameter will control the number of points that you add. So if you make it such that it needs to add at a very low density gradient, then it will add a huge number of points. If you make that density gradient very large, it will add a smaller number of points. So this gives you some control as a user. So this is to illustrate how this is done. I'll spend some time on this slide. So initially, let us just look at one edge, two cells, cell 1 and cell 2. So I have here 5 edges. So I've listed it out here. So I've defined these edges as edge number 1, 2, 3, 4, and 5, and defined that edge 1 connects node 1 to node 2, and it has adjacent to it cell C1 and C2. Similarly, edge 2 connects node N1 to N3, and it has on one side cell C2, the other side nothing. This is outside, that is outside the domain. Similarly, edge 3 connects N1 to N4, and on one side it is outside the domain, on the other side it is cell C1. And similarly for edge 4 and edge 5. So this is my initial grid. Now, after the solution, I decide that edge 1 has to be refined. So I add to that edge one new point called N5. At the center of this edge, I will add a new point called N5, and I will determine the X and Y coordinates of that point and add that to my list of coordinates. So whatever points I had 4 points initially. I will create point 5 and I will add the edge, the X and Y coordinates of that point. Then I will modify my connectivity matrix. So now if you see carefully, the number of edges has increased. So I've gone from 5 edges to 8 edges, and the adjacent cells, initially there were only 2 cells. Now there are 4 cells. So I've defined these new cells called cell 3 and cell 4, and cell 1 and cell 2 as is shown there. And now I will modify my connectivity matrix. So initially when you looked at edge 1, it connected N1 to N2, and I had cell C1 and C2 adjacent to it. Now I will define edge 1 to be the edge which connects N5 to N2. N5 is the new point, and it has C1 and C2 adjacent to it. Then I will define the next edge which connects N1 to N3. No point has been added, but the adjacent cell has changed from C2 to C4. Edge 3 connected N1 to N4. Now instead of C1, it is C3. Similarly for 4 and 5. And 3 new edges have been formed, which are 6, 7, and 8. So you define how these edges connect N1 to N5 with adjacent cells. So what is essentially being done is that by adding one extra point, I just need to make these changes in the local connectivity matrix, and my grid is redefined. And this process can be repeated edge by edge. So if you incorporate this into your flow solver, as and when the flow solution is obtained, you can do a round of grid adaptation, maybe do some grid smoothing, and then continue the solution. Okay, so I've already explained this, but wherever I've got an asterisk, it means there's a cell which is outside the domain or not shown in the figure. So in a general case, this will be part of a very large grid. It may have millions of cells, but you only need to make these few changes. And the rest of the connectivity matrix will not be changed, and that is all that is needed. So as I've explained, there is a new point N5. You have to add these coordinates to the list of points, and then you can add 3 new edges at the end of the earlier list of edges. See, one thing about the unstructured grid data structure is that it doesn't matter where you add the point, because the point numbering, it's not that point 3 has to be next to point 4. Point 3 can be in one place, point 4 can be somewhere else. As long as you define your connectivity properly, there is no issue. So, of course, when you do this approach, you can get some skewing in the cells and do some smoothing so that the skewness is removed. And you can divide the cell in many different ways. I've just illustrated one way to explain how this happens. But you can take the cell and subdivide it into 3 different cells. You can add a new point at the centroid of that cell. You can do many different things. But essentially, the point that I'm making is that only local connectivity changes are required. So it is much easier to add points in unstructured grids. So to illustrate how this helps, I'll just give one example where initial grid and pressure contours are shown, and then how the refined grid and pressure contours to show the change. Okay, so this is an example where I have got 2 airfoils, one below the other, and one initial grid has been generated, where you can see that in the region of the leading edge of the airfoil, there is some clustering of the points, and then near the trailing edge, there is some clustering. And then based on the Delaunay triangulation, the cells in the vicinity of both these airfoils are small. And as you move away, they become larger. So this is the initial grid. This is based on the distribution of grid points on the boundaries. So normally when we solve such a problem, the outer boundary will have very few points. The 2 airfoils will have a larger number of points. And because of that point distribution, the initial grid has some difference in the grid sizes, and this is how it comes. Now, if you solve the flow past this grid using a KFVS finite volume method, you get this flow distribution. So these are the density contours. So now you can see that there is some kind of a shock wave formation at the trailing edge of the upper airfoil, which hits the lower airfoil at this point. And then on the lower surface of the lower airfoil, there is another shock wave which is formed. Now, if we do that adaptation technique that I was explaining in detail earlier, you will get a grid like this. So if you look carefully here, you will see that in the regions of the shock wave, grid points have been added. So what has been done here is that based on the initial solution, the density gradient at each edge has been evaluated. And then based on that density gradient, the flow solver decides whether that has to be adapted or not. So the gradients will be high in the initial nose region of the airfoil and in the shockwave region. So now if you look at the refined grid, you see that in the region of the shock, a large number of points are added. And now if you look at the solution, you will see that the flow pattern, the shock pattern is captured much better. In fact, the upper airfoil at the back, you can very clearly see a triangular shock pattern that has been captured. And this has been done using grid refinement. So here, as I explained, an initial grid generated using Delaunay triangulation. Based on that initial grid, you have generated a solution. Based on that solution and the adaptation criterion, you adapted the grid, done some grid smoothing, and regenerated a solution, which is capturing those shocks better and is a more accurate solution. So with that, I think I'm coming to the end of my talk. So what I have tried to do in this lecture is try to give you some ideas of the different methods that can be used for grid generation. Now, numerical grid generation itself is a major field, and this is only a very brief introduction to the subject. So that is meant to give you an idea of what you should read. So I am hoping that whoever is participating in this course, you will get some motivation to refer to further material on the subject. One thing that I will add is that now there are so many grid generation packages, commercial packages that are available, that very few people will actually need to write a solver of their own. They will tend to use these packages, which sometimes come bundled with the software, flow solver software also. But I feel that if you are going to use these packages effectively, then you should understand the methodology that is being used to generate those grids. And if you understand what you're doing, it is you'll be able to more effectively use these packages and get good solutions for your grid generation problems. Okay, thank you. That is the end of my slide lecture.
Thank you, sir. So, participants have given some questions in the chat.
Okay.
That will be discussed. Okay, forgive.
Hello, the first question goes from Amlan Kumar sir. He used to ask that for the analysis of wind tunnel load on the complex CFD building model, what type of grade is suitable?
What was the question?
For the analysis of wind load on the complex CFD building model, what type of grade is suitable?
What type of grid is suitable?
Yes, sir.
See, normally I would say now that for most of the complex geometries, people are using unstructured grids, mainly because two things. One is it is faster to generate the grid. And secondly, you can do this grid adaptation easily. And now there are multiple solvers available which can do unstructured grids. So I would think that if it's a complex shape, it is better to use unstructured grids.
Okay, sir. The next question is from Manish Kumar sir. Which is the best software from grid generation?
The best?
Best software for grid generation.
Okay. See, I cannot say that this is the best or that is the best. Many of them have the same features. But what is happening now is that many of the commercial solvers come with some basic grid generation software within the solver itself. So that is, it comes as part of the package. But the software I am familiar with, the one which is from Pointwise, is a very good software. But I don't think I can give you an answer that this is the best one that you can buy. But based on the requirements of your, see, for example, if you only want to do unstructured, then you need not look at a package which has got multi-block. So that's not a question I can give a direct answer to.
Thank you, sir. The next question from Burma, sir, is what is the criteria for grid generation at fluid-solid interface?
See, when you are doing fluid solid interactions, what is going to happen is that the solid part, which is the boundary for the grid, for the CFD part, is going to move. The boundary will change and it may move in space also. So your grid has to either be regenerated when the shape has changed, or you have to move that grid so that it conforms to the new boundary. So if you are doing unstructured grids, then it is quick to regenerate. So if it is a fluid structure interaction where there is a very large change in the shape or the position of the structure, then it is better to use unstructured grids and regenerate the grid. But if it is something where the movement is not too much, then you can essentially reposition your grid points so that they conform to the new structure. So it depends on the problem.
The next question from M. Aruna. For analysis of ventilated welding, which grid is suitable?
For analysis of
Ventilated building.
ventilated building.
Yes, sir.
Yeah. See, again, now, whenever you're talking about some very complicated shapes and sort of complex flows where you would need to do adaptation, then it is better to go for unstructured grids. Because when you're talking about flow in a building, there will be some gradient somewhere, there will be some vortex formed somewhere. It is easier to handle those sort of flows with unstructured grids and adaptation of grids.
Correct. Good.
Hello, sir. The next question is, when rotor is moving in a loop in 3D, so how the grid is moving and what is the criteria, mathematics behind it?
In a problem where you have a rotating rotor or propeller, normally you will generate one grid which is moving with that rotary object. So if it is a propeller or a rotor, there will be one grid which is moving and there will be the rest of the grid which is stationary. And then you have to interpolate the solution between these two grids. I'm assuming you're talking about a body where there is a fixed body with a rotating part. So normally what you will do is the rotating component, you will have one grid which is rotating with the body. And then this grid will interact with the rest of the stationary grid appropriately. So that is normally how it is handled.
Okay. The next question is it possible to generate a grid without skewness? What is the effect of skewness error in the result?
See, the skewness will, you can't say that can I generate a grid without skewness, because it depends on the sort of geometry you're dealing with. If you have something which is absolutely straight, if you have a cube, there is no skewness because the grid lines are straight lines. If you have something close to a cube, but if you have something where you are mapping an airfoil into a cube, then obviously the grid lines are going round the airfoil and there will be some sort of a skewness. So the more skewed your grid is, the more inaccuracy there will be in your solution. Because see, any flow solver does interpolation from you will store the values at one of the points or at the cell center, and then to calculate gradients, there is some sort of a finite difference done. So all that will become less accurate if your grid lines are skewed. So there is no way to say I will absolutely eliminate the skewness, but many of the grid generation packages now, they will give you a measure of skewness and whether there are any negative volumes in the cell. That happens because sometimes the grid lines will overlap and it will give you negative volume instead of positive volume. So all those things have to be looked at. You have to make sure that with smoothing, some of the smoothing packages that are there, you try to make your skewness as less as possible. But there is no way to eliminate it, and it does have an effect on your flow solution.
The next question is about, there's a question called, does grid structure also depends on Reynolds number of the flow?
It depends on the Reynolds number in the sense that if it is a highly viscous flow, you need to be able to capture those viscous layers. You need to do more concentration of grid points there. So if you're dealing with viscous flows, then you have an idea of what is the boundary layer thickness. So you will concentrate your grid points in the region of that. If you're doing a flow with very little viscosity, then you need not have so many grid points. So as I said, that when you do this grid generation, you have to have some idea of the sort of flow you're expecting and tailor your grid to that flow. So if you're doing viscous flow and there is a wake, then you will define a wake, concentration of grid points in the wake, concentration of grid points on the surface. And that is how you do the initial grid. But as I showed in the adaptation, they see sometimes there are gradients within the flow like shock waves, which you do not know at the time of solving the problem. So then when you have solved the problem, you have to do this sort of adaptation and capture those things.
There is another question, sir. Can you please throw some light on the checkpoints for correctly generate grid in CFD?
See, checkpoints are mainly, the first thing is that when you are defining your grid point distribution on the boundaries, then for example, when we define grid point distribution on an airfoil, we will concentrate the grid points on the leading edge and towards the trailing edge, because we know that there are gradients expected to be higher gradients there. So the first thing, of course, is that on the boundaries, you define your grids, your points appropriate to the flow, because you will have some idea of that. Then once you have generated your grid, then you need to check the grid quality, which will look at things like all volumes positive, grid skewness, aspect ratio of the cells, and those things. So this is actually what you can do before you have got the solution to generate as good a grid as you can with the information that you have. But after that, it is, finally, if it gets you the right solution, it is the right grid for the problem.
This is the last question, sir. How to solve moving grid problems?
How to solve?
Moving grid problems. Moving grid.
No, moving grid problems means you see there are two ways to handle a moving grid. One is where it'll be sort of overlapping. That is, one grid there will be a background grid, and then there will be a moving component with a grid which is moving. So then you have to interpolate between your moving grid and the background grid. So generally that is what is done. For example, supposing you have a store which is being dropped from a body, then you have to either regenerate the grid every time in the new position, which is possible with unstructured grids, but it takes time. Otherwise, you have to have a grid which is moving in the background grid. And then at each point in time, the connectivity with the background grid will change. So that interpolation has to be done properly.
Thank you, sir, for
Okay.
your giving this session, highlighted sessions. I hope participants has taken the points, important points from this grid generation topic. Now I like to introduce our Shekhar Majumdar sir, to uh, talk something about your working at a place and how it is, so that we can discuss. I invite Shekhar Majumdar sir to speak out.